In this video, we will be explaining on our project, which is a wireless charger. Wireless charging is the transfer of power from a power outlet to your device without the need of connecting cable. It involves a power transmitting pad or stand and a receiver, which is usually built into the phone itself. Now, allow me to explain the principles involved in wireless charging and how a wireless charger is built. Here we have a copper wire. If I apply voltage to its end, current will pass through the wire. This current flow will create a magnetic field around the wire, and these magnetic fields are not only in one zone, but is created around the wire in a circular way around it. And I hope this animation will help you understand the concept. But now if I wind this copper wire around the loop, what happens? As you can see, the magnetic field revolving around the wire are now merging together. In this way, we will have a maximum magnetic field in the middle. And if I make even more loops, the fields are summing together more and more. So that's how, in a manner of speech, we can center the power in the middle of the coil. But this is not the magnetic induction yet. This is the reverse process. So if I apply current to a loop, it will generate a magnetic field. But if I do the opposite and apply magnetic field inside a loop, it will induce current into the wire of that loop. So this is called Faraday's law of induction, but there is more. A static magnetic field won't induce current into the secondary loop. Here, with my function generator, I apply fast pulses to the primary coil. Now, I take the secondary and connect an LED at the output. The closer I get to the primary, the brighter the LED will get. So we are sending power wirelessly, and there is no connection between the supply and the LED. But still, the LED is turning on. So far, so good. But this is not as easy as connecting the smartphone directly to the coil. Why?
Well, first of all is the voltage. Smartphone charges at 5V DC voltage. The output at the secondary is oscillating, so this is AC. At the same time, we don't know the output voltage from the secondary. It could be higher or lower than 5V. And also, if I move the coil, the voltage will change, but the smartphone needs steady voltage. So to make the transmitter circuit, the coil and the capacitor here will create the LC tank, and using a MOSFET, we can keep switching the coil, and this will automatically create the resonating frequency. I mount the simple circuit on a PCB with the coil at the output. Now let's talk about the receiver.
To charge our electronic device, we need DC voltage. That is why the first component we need after the coil is a full wave rectifier that is made up of 4 diodes. This will pass from AC signal to only positive pulses. A capacitor is added as a filter to the output of the rectifier, and it will charge up and give us a steady DC voltage. Now, let's talk about the turn ratio.
If the transmitter and receiver has the same amount of turns, the ratio is 1:1. So, the voltage at the receiver output should have the same as the transmitter. If you want a higher voltage, you should increase the secondary loops, which in this case, 1:5.
So, in order to have a constant output, we need a voltage regulator. For example, we can use an IC7805 and regulate the output at 5V DC. And here we have the 5V IC7805 regulator.
Now, as you can see, I couple the transmitter with the receiver. The output is now regulated at 5V. Even if the receiver voltage overpass its 5V, the output now is always 5V. So now, I have my steady DC voltage that we could connect to the smartphone, input and charge it. And there we go, we can now charge our smartphone wirelessly.